You'll recall the Venn diagrams, and we had Venn diagrams for mutually exclusive and non-exclusive events. These are two mutually exclusive events. So I just put this up again because this really theoretical looking thing here, we're going to use it later in class today, and you will be using it lots. So in non-exclusive events, when there's overlap in the Venn diagram, for example, having cancer, having heart disease, something where it is possible to have both, then we use this intersect symbol to represent the intersection between those two events when both of them happens, the and. And then we had some slightly different rules in this case, and these you're going to use less in this class. You should know about them, but when it comes to using probability distributions for the purposes of inference tests, usually it's going to be exclusive events. It's going to be your null hypothesis and your alternative hypothesis. Those will be your two possible truths, and they're mutually exclusive. So these you should know, but I won't review them again in detail. Here again is all your probability notation. And I'm going to skip over those for the sake of time. So on to the new stuff. Any questions first about the probability notation stuff? Okay. So a random variable, I guess it sounds like either a simple thing or a complicated thing. But the way that we take it to mean in this class, it's anything where there is at least some uncertainty in it. So when we talk about having cancer or not having cancer, if it is after you've had the gold standard test and you know that is a realization of a random variable. If it's at some point where you don't know whether you have cancer or the disease or not, and you're about to get a test, then you can think of that as a random variable. And the case that we're usually going to take it in is talking about the probability of that event occurring over many people. And that will be our random variable. So, for example, the number of new cases of diabetes in New York City in a given year is a random variable. It's something that there's some finite probability in any given individual person, and summed up, that number is at least partly due to chance. There might be specific risk factors or things that contribute to it in a non-chance way, but there is at least an element of chance, so it's a random variable. Or the weight of a randomly selected individual in New York City is a random variable because you can pick anyone. Their weight could be anything within some range, and you could describe that probability of weight as a random variable. So we're not talking about one realization, we're talking about the unknown in the random variables. We actually covered some of these already, the types of variables, and without getting into it at the time, we were really talking about random variables, the categorical, the discrete, and the continuous random variables. All of those were things that you could measure, say, on an individual, and at that level, it's not random after you've measured it. But if you're talking about the aggregate distribution among many people, then it's a random variable. So just some notation, and this is also noted in your syllabus. We're going to use uppercase Roman letters for random variables, and we'll use lowercase for particular realizations of that variable. So if we're talking about the height of individuals, that might be an uppercase X, and if I were to then measure the height of everyone in this class, those would be lowercase x1, x2, x3 to indicate records or realizations of that random variable. So just a few examples here. Blood type, if we're talking about the blood types of everyone in this room, that's a random variable because I don't know what they are, but I could say something about the probabilities based on the probabilities that have been observed in large groups of people. So what kind of random variable is that? It's categorical, of course. Or the number of visits to the obstetrician's office during an uncomplicated pregnancy. What kind is that? Discrete, yep. Yeah, so you can think of this as, so these fractions of women are something that has been averaged over many, many women. The distribution of body mass index in a population. How about that one? Continuous, yep. Okay, so let's start with continuous random variables. We're going to describe the distribution of a continuous random variable by this thing that we call a probability distribution, or the probability density. And here's a couple examples. What they look like is we're going to have all the possible values of that variable on the x-axis, and then we're going to have a probability on the y-axis. So here's an example of commuting time in minutes. So if we were talking about how long it takes Hunter College students to commute to campus, this might be something that is based on collected commuting times from a survey from thousands of students. And based on that, for every possible value, or every possible value, it can't be less than 0. And I guess it could, in theory, be infinitely large, but it would taper down to 0 at some fairly large number of minutes. This describes the probability of that being someone's commuting time. So, it's got a peak here, in this case at about 15 minutes. This is probably, I don't know, at a campus that's not in New York. But the important thing is that you have a probability for every possible value, and more importantly is you can calculate a probability for any interval along this curve. So the probability of having a commute time of 45 minutes or greater can be calculated by this area underneath the right-hand tail. And for any interval like that, you can calculate an area, and that area will be a probability of interest. So it's not so much the actual values of this probability here that are going to be of interest, it's the area under intervals, and you're going to get lots of practice calculating those. Each of those intervals has a probability between 0 and 1. You can't have any probability less than 0, right? You can't have a probability greater than 1 either. It's got to be between 0 and 1. And the interval containing all possible values in the commuting time example from 0 to infinity is equal to 1. The total probability is equal to 1.